Okay, great. It's a great pleasure to introduce our last speaker this morning, Victor Nistor from Institut Elie Cartan de Lorraine. His title, you can see Localization and Cyclic Cohomology of Cross Products with Algebraic Groups. Victor, please.
Thank you very much. It's a pleasure to be in Toronto, even if only virtually. Also, I'd like to thank you for being here in your hearts, of course. Some of you are in Toronto, I assume. Also, I'd like to thank the organizers for their hard work and for the opportunity to present my results. So the title of my talk, which I repeat here, is Localization and Cyclic Homology of Cross Products with Algebraic Groups. Now, as the title suggests, I will talk about Hochschild cyclic and periodic cyclic homologies of A cross G with G real algebraic group. Now, here I'm not making these definitions very, very explicit. It's just a glimpse, but we'll come back and I'll make them more explicit. However, if you really wondered, let me say that the class of real algebraic groups certainly encompasses the class of compactly groups, so they are there, as well as the classical groups that we are used to study. Okay, so the method that I will use will be a localization with respect to maximal ideals of the representation, the ring of class functions of our group. These are just, you can call it some sort of representation ring. It's the class of G invariant smooth functions. And also I will mention some connections between this localization that I have just mentioned and completion, as well as orbital integrals. I will begin my talk proper with an introduction that will aim at putting the results of this talk into a historical perspective. And since we are celebrating 40 years from Kahn's talk on cyclic homology, and since also these results are at least 30 years old, more than 30 years old, I hope you will forgive me if I will indulge in some reminiscences. For instance, 1981, the year that we are celebrating, also marks the beginning of my life as a research mathematician. That was in Romania. And that time there were some study groups, one in algebraic topology, one in scattering theory, and most importantly, one in operator algebras and K-theory. It is the most important one since it was run by Dan Voiculescu, who eventually became my advisor. Now, these study groups provided some very fortuitous circumstances for appreciating what at that time was the emergence of non-commutative mathematics. And in fact, two mantras were common at that time. One was that C-star algebras are non-commutative spaces. Now, you may have heard this many times. What does it mean? Well, it means that the category of C-star algebras contains the category of locally compact spaces. Also, another mantra was that K-theory pertains to non-commutative geometry. Well, it wasn't clear what non-commutative algebraic topology, sorry. Well, it's not clear, it wasn't clear what non-commutative algebraic topology was at that time, but certainly we knew something that was there, that is K-theory. Okay, and getting a little bit closer to the subject of my talk, some of the things that I learned from these study groups were that C-star algebras provide a convenient framework to study at the same time locally compact spaces and locally compact groups. So there was no longer any intrinsic difference between the two. Also, I have learned that identifying the K groups of group C-star algebras or their cross products is an important question that would complete a program started in algebraic geometry. And I must say that, of course, this is related to the celebrated Baum-Cohn conjecture, but at that time I didn't know about it. Okay, in this series of events, a turning point was Voiculescu's suggestion to study Cohn's article, C-algebras and non-commutative geometry. Now, this is an article written in French, and I have recited the title in English, but you have here also the title in French, C'est toi l'algèbre géométrie différentielle. And I really like this talk, this paper, sorry. I also like the talks, but now I'm talking about the paper. I really like this paper because it combined, on the one hand, Riefel's non-commutative tori, about which I learned from the papers of Pimster and Voiculescu, and especially since it made the desired, the expected jump from non-commutative topology to non-commutative differential geometry. Okay, so this paper of Allen, as well as the works of Pimster and Voiculescu, what was motivated me to study the cyclic homology of cross products. Well, that was in Romania. I was fortunate, nevertheless, to get a hold of some papers of Baum, Burghela, Cohn, Karoubi, but sadly, some important papers of Fagin and Tsigan and Berlinski were not available. Well, this is a historical talk in a certain way, so now it may seem hard to believe, but there was a time when one was doing mathematics without email and without internet. And that was, these times, these were the times then in Romania. Okay, so I'll basically finish my reminiscences, except for a disclaimer. Since these results and the spirit of the conference is a historical one, I will concentrate mostly on the results available at the time when they were obtained. That is at least 30 years ago. But that doesn't mean by any means that there were no important recent evolutions. And actually, we have seen in many of the talks in this conference results that are much more recent. Okay, so I mentioned here just some names. Also, the last disclaimer is that if there's no reference to a result, doesn't mean that I claim it. Okay. Okay, so what is a cross product? Well, to define, we look first at the discrete case. To introduce the cross product, we start with a complex algebra. We consider also a group, which when it's discrete, we'll call it usually gamma, that acts by automorphisms of A. That means that we have such a morphism. We'll take unital automorphisms if the algebra has a unit. Although eventually we're interested in cross products by certain Lie groups, it certainly helps to look a little bit at the case of discrete groups. So the cross product algebra A cross gamma for gamma discrete is, as you know all of you very well, the algebra generated linearly by symbols of the form A times gamma, with A and A gamma in the group, and with the following twisted multiplication, which basically means that gamma implements these automorphisms, the inner automorphisms implemented by the group is this morphism alpha. Okay, so it's a well-known formula. And also, maybe to make things a little bit more concrete, in the case of a discrete group, A cross G is, as a vector space, simply the algebraic tensor product of A and the group algebra. Of course, that will change. And later on, when G will become a Lie group, this will rather be CC infinity of G with values in A, but we'll get to that later. Okay, so it was mentioned already in this conference that it's important to look at other conjugacy classes than the identity. And here's a basic observation, which, well, I hope I'm not wrong, has been some time, due to these people. And the observation is that starting with the Hochschild complex of A cross gamma, that this complex decomposes as a direct sum of some complexes indexed by the conjugacy classes of the group. Okay, quickly take a look at this. It's a little bit computational, but that will tell us a little bit what's going on to make things more concrete. So the Hochschild complex is the one that you have seen. We take tensor products of the algebra with itself. B is the Hochschild differential. We have seen that, if I remember correctly. I will denote like that with gamma in these brackets, the conjugacy class of some element of the group, and it's given, of course, by this formula. And then the subcomplex associated to a conjugacy class, to the conjugacy class of gamma, is generated linearly by the tensors of the form A gamma 0, A gamma 1, A gamma k, such that the product of the gamma terms is in the conjugacy class gamma. This, of course, holds also for the cyclic complex and periodic cyclic. In fact, many things in my talk will work for all these cases, and I will choose whatever is more convenient to illustrate. Well, again, let's just very quickly see that this is a subcomplex. Now, if you remember, and this is in fact important because it's related to cyclic objects, the Hochschild differential is generated by taking certain products of adjacent elements. In this case, the product of the I and I plus 1 components. Well, if we do that, in fact, we can ignore the A part and we look at the gamma part. And if we make the product, which we said has to remain in the same conjugacy class, we see that actually this product doesn't even change. Well, that will not be true in general because if we look at the last differential with the last D, which brings AK gamma K all the way up in front, then when we take the product, the gamma K from the back has moved in front. Okay, so here I'm taking the product of the last element times the first element, and I get this for the gamma factors. The gamma K has disappeared here. Well, in any case, so we see that this is, well, it's not the same thing as gamma in general, but it's nevertheless conjugated. And very importantly, but it's the same calculation, so I'll skip that. This is also necessary, this conjugacy class thing is also necessary for the cyclic permutation, which plays such an important role. But the calculation is the same. Okay, having this direct sum decomposition of complexes, we get a similar direct sum decomposition of the corresponding homology groups. And that again holds for Hochschild, cyclic, and well, with a little bit of care also for the periodic cyclic, because have a projective limit there. Okay, here's that anticipated direct sum decomposition, and this is what I have just said. Now for cohomology, we'd have to replace direct sum with direct products, again being careful for periodic cyclic homology. And it turns out that in fact, it does help to look at the gamma parts. We'll get to this again in a moment, because one can say something in terms of gamma about these parts usually. But right now I want to ask myself how to extend this to non-discrete groups. And my answer will be to use localization. Okay, and that I'll explain. Okay, so we like these conjugacy classes, the components corresponding to conjugacy classes, because one can use for them standard techniques from homological algebra like localization, derived functors. It's a Tor, it's still a Tor functor. And at least in certain cases, it's based on the centralizers, which we presume we know. Okay, let me remind what happens, for instance, in the case when A is the complex numbers, in which case our cross product is nothing but the group algebra. As I said, the centralizer of X will, of some of elements will play a role. I'll call this the element here X, not to have too many gammas. And gamma X is the set of elements that commute with X. Okay, and at least in the case that I am talking about now, that of group algebra, the gamma components of all these groups can be expressed in terms of the group homology of so many groups. So the homology of the group gamma divided by the subgroup generated by gamma. Okay, don't want to spend too much time on this, but if you are a little bit familiar with group homology, you will see that this will result in a different behavior for torsion and non-torsion gamma, basically with a case gamma torsion case that can be ignored. Okay, so this is going to be a recurring theme. Okay, and I have already used localization and probably I used it already in several senses with different meanings. And in fact, turns out they are the same. So I'll use localization in the proper sense of commutative algebra. And let's quickly explain why this is the case. So all these gamma components are in fact obtained by localization. So that's why we will be looking at localization. So very quickly, if we have a ring, a maximal ideal M in R, here's a crash course in commutative algebra, and M is an R module, then the localization of the module M at the maximal ideal Gothic M is given by equivalence classes of fractions F divided by S, with F in the module and S not in the maximal ideal. That's a multiplicative set, and it can be written like that as a tensor product. So it's enough to know how to localize our ring. Okay, and why is this relevant in our case? It's actually relevant in many situations involving cyclic homology. Is the following result, which is very classical, but it's very nicely explained in the book of Atiyah and McDonald. And it says that if we have an R morphism F from M to M prime, which that morphism will be an isomorphism if and only if all its localizations will be isomorphism. Localizations with respect to maximal ideals, of course. Okay, so that's a basic result in commutative algebra. In the case at hand, that of discrete groups, we will look, in fact, for all groups, we will look at class functions, which will be, in all cases, C infinity of gamma, so smooth functions on gamma that are gamma invariant. Now, since gamma is discrete, these are just all invariant functions. And I'll have to isolate here for some technical purposes, which you can basically ignore, an ideal of R gamma, which is the class of the set of class functions that are supported on finitely many conjugacy classes. Some sort of analog of compact support, except that compact support may not make sense. Then, given a maximal ideal, if that maximal ideal does not contain this compactly supported in quotes function, then we can say what it is. It is simply the set of functions that vanish at some gamma, and we are basically there. Let's use this observation for a module which, over the ring of class functions, is a direct sum of modules indexed by the conjugacy classes. These are essentially all of them. If we take a maximal idea of the form that I have just introduced above, that is functions vanishing at gamma, then the localization at this maximal ideal is simply the gamma component of M. And if your maximal ideal is one of the funny ones that contain RC, then in fact the localization is 0. Well, we have to put them to have correct statements, but basically we can always ignore this type of ideas. Okay, and I want to start to use this idea to study the homology groups, and then by particularizing to the case of the Hochschild homology of A cross gamma, we see that what was the gamma component before is simply the localization in the sense of commutative algebra that we have discussed. So it's the localization of the Hochschild homology of A cross gamma with respect to the maximal ideal. And this is going to be the path that I will follow also for continuous groups, because it makes perfectly sense for continuous groups also. And I said that most of what I will say holds both for cyclic and periodic cyclic homology, in particular this statement. Okay, as I have already said that we'll use a similar approach for cross products with Lie groups. Okay, and this already tells you, it already gives you an idea why algebraic groups, and the answer is that algebraic groups are known to have nice conjugacy classes. Well, other groups do too, so the method doesn't restrict to algebraic groups, but it's easier to do it in that setting. Okay, so let's get closer to the main results, which is for algebraic groups. As I said, algebraic groups have nice orbits. They also happen to have nice, a nice ring of class functions. We'll see examples when this is not the case. So here's a here's a second crash course, this time in algebraic geometry. So let's assume that K is an algebraically closed field. Then a K alpha, an algebraic variety in Kn, is the set of common zeros of a set of polynomials in K of x. Can even choose this set finite, but that's not important. By the way, this doesn't happen in C infinity, in the C infinity case, but it happens in this algebraic case. And we will need the varieties defined over a subfield and their rational points. So let's assume that we are given a smaller field, because usually these algebraic closed fields, especially for p-adic groups, are kind of more complicated. And then we say that our variety is defined over little k if we can choose our set of defining polynomials to have coefficients in little k. And then its k points will be the set of points in the variety that happen to have coordinates in the smaller field, little k. Now, of course, there's a dual definition in terms of algebras. In that case, the points of V identify with maximal ideals, which tells you that maximal ideals something good to consider. Okay. And now what is an algebraic group? Well, we know what a Lie group is. By analogy, an algebraic group is, that's probably not how people introduce them, but that's a good way of thinking about it. So an algebraic group, bold G, is an algebraic variety, which is a group, okay, of course, and such that its group operations are the right functions in our category. That is rational or algebraic functions. Equivalently, and this relates to other talks, is that K of G is a suitable Hopf algebras. And here are some examples, but remember that we're actually interested in the little k points, okay? So we have SLN of K, GLN of K, all these classical groups. I have already said that the compact Lie groups are in fact real algebraic groups, and here we have a nice equivalence of categories. Okay, and when I will talk, I will mostly talk about real algebraic groups. And in that case, the big field, the field that is algebraic closed, is just the complex numbers, our good old friend complex numbers. And the little field is the reals. Okay, so these are examples of algebraic groups. I'll need some more examples. The example of the Heisenberg group is easy, but I'll need it next. Okay, so it's what you know very well. I take the smallest dimensional Heisenberg group. It's diagonal matrices with one upper diagonal matrices with one on the main diagonal and entries in R, because I said we'll in fact take the real points, the rational points. Okay, at this point, maybe we wonder if there are any groups that are not algebraic, right? So many turned out to be algebraic. Well, actually, there are some that are not algebraic, and here's the first example. So let's take, let's consider a discrete central subgroup of our friend that we have just seen, the Heisenberg group. Then the quotient H3 by Z is not algebraic. So here Z has to be discrete, central, non-trivial. Another maybe more interesting example is that of the universal cover of SL2R. Also, well, the discrete groups are generally not algebraic because they have too many components, unless they have finitely many, and then they are algebraic. So the only discrete algebraic groups are the finite groups. Okay, and here's now a more interesting example that will show some pathologies that, well, as we see, will arise if one considers non-algebraic groups, and that's related to consoliations and to the Riffle's non-commutative tori. And it's kind of this funny-looking solvable Lie group. So we notice on the diagonal the factor e to I t and e to I theta e. Since we are taking theta not to be rational, t will be determined. So in other words, we have the quotient by the radical is just the real numbers. Okay, so this is not real algebraic. This group is not real algebraic. And I'm giving you this example because, as I said, it exhibits some pathologies. One is that its conjugacy classes are highly non-separated space. Well, we happen to like this in non-commutative geometry, but for the purpose of my talk, that's not good because the ring of invariant functions will be not big enough. So this doesn't happen in the algebraic case. Another thing that doesn't happen is that some conjugacy classes are not locally closed in F theta. It's one of the basic properties of algebraic groups that their orbits, if the action is algebraic, of course, rational, are locally closed. Very nicely explained in Boileau's book. Okay, now let's get back to cross products after so much algebra. These algebraic groups are always smooth in whatever sense you want, even if they are defined over p-adic fields, but smooth as algebraic varieties. In our case, a smooth real algebraic variety will be actually a manifold, so our algebraic groups will be Lie groups. Okay, and some constructions do work. In fact, many results do work in the general framework of Lie groups. So assume we have a Lie group, let's form the cross product. So it says in the discrete case, so we have a Lie group, it acts on an algebra A by automorphism. We assume that A is a complete topological algebra. We also assume that alpha G is continuous and unital for each fixed G. And then if we fix, on the other hand, A and let the little g vary, this is going to be a smooth function on the Lie group. Okay, and the smooth cross product is then just CC infinity of G with values in A. We have already defined that, right? So if G is discrete, it would be the same thing, of course, but for G non-discrete, this is more complicated. And here's the formula for the convolution product, which you know it's not very important for us. So I'll move on. And we want to say something about the cyclic homology of these groups. And one of the reasons is that even in the case when A is equal to C, this has to do with the duals of, with the dual of the group. I'm saying duals because depending on what group you have, you will have a different type of quote unquote right dual. So assume A, so we are looking at A cross G with G some k points of some algebraic group. Will work, as I said, mostly in the case when our group is defined over the complex numbers and we take real points. But let me say even here, I'll just make another comment at the end. So let me say right away that actually the p-adic case, it's much simpler. Okay, okay, so the first question that we want to ask when computing the cyclic homology. Do you hear me well, by the way, because I changed position?
Yes, I can hear you well.
Okay, okay, thank you. Just checking. So I did that while teaching so many months online. So I think this is always a good thing.
Yes.
Okay. Now, the right choice of tensor product is, in fact, a delicate analysis question, and there's too much to say about this here, but there are some very nice and very detailed analysis by Kunz, Meyer, and others. What I will do to make my life easy, well, after 30 years, want to make it easier, is that I will choose the most straightforward cyclic object. And this is defined using projective tensor products, but I don't want to get into the discussion what's a projective tensor product for CC infinity. Okay, so I'll just take as an ansatz CC infinity of Gn plus 1 for the component in G, but the component in A, well, that will deserve to be hit with a projective tensor product. Okay, so this happens to be a choice that works. Maybe others work as well. And in analogy with what happened with, in the case of discrete groups, so this is an important point of this development, is that this cyclic object is in fact a module over the ring of smooth class functions. It's exactly the same computation, right? You just have to dualize it, but it's really just the same calculation. There's really no glory in this observation. So we look, as we did in the discrete case, at the maximal ideals of Rg. And there, if you remember, we had to exclude certain maximal ideals. In fact, they were trivial in a certain way. And in this case, if we exclude those maximal ideals that are at infinity in a certain way, then all other maximal ideals will be given by functions that vanish at some element gamma. And here's a surprise, in case of a algebraic group, I mean, we have, it must better be algebraic. This gamma is a semi-simple element. This has again to do with the structure of conjugacy classes in algebraic groups. So it would be a little bit nuisance to write the conditions that a Lie group would satisfy here, to have something like that. So here, having an algebraic group certainly is convenient. Okay, so I said we kind of exclude the maximal ideals that are not at infinity. They are, we don't even have to describe them because they kill everything. So that would be the analog of the RC. Rigorously, they are the closed maximal ideals. Okay, so let's formulate a result after so much introduction. So we'll be in the setting that we considered for the last few slides. that is, G will be the set of real points of a connected real algebraic group, defined over C, of course. Since the group is connected, it may have more real connected components than algebraic ones, but that's not important. It's by finite factor. And G, since it has a finite number of components, okay, so it will have a maximal compact subgroup. Okay, okay, so G itself, not just its algebraic shadow has to be connected. Okay, well, it has been 30 years. Okay, so then the result is that the Hochschild cyclic and periodic cyclic homology groups of A cross G are G modules. This is easy. And in general, for the other homologies than periodic cyclic homology, the situation is pretty complicated. One can say something, but it's not nearly as neat as saying that the periodic cyclic homology of A cross G when localized at M is the same as the periodic cyclic homology of the cross product by one of its maximal compact subgroups. They are conjugated up to a shift, which is the usual that one remembers from the Kohn-Kasparov conjecture, and localized still at M because we can restrict class functions on G to functions on K. Now, if you wondered about these weird maximal ideals, in fact, once we localize at them, so the ones at infinity, once we localize at them, this is going to kill the cyclic homology. And in fact, this cyclic homology group, periodic cyclic homology group, will vanish if M is not elliptic. That is the semi-simple element to which it corresponds is not conjugated to K. Okay, and the proof is actually relying really heavily, so I'm not going to give it. It's relying really heavily on cyclic, pre-cyclic, and quasi-cyclic objects. Now, why is that? So we kind of, as in the discrete case, we kind of take a resolution of the complex with some sort of free G module. And then we know from the work of many people that the structural morphisms of the cyclic category lift to this resolution. Okay. However, if the group is non-discrete or A is non-unital, there might be a problem with degeneracies in the simplicial structure. So that's why we'll get only pre-cyclic objects. So pre-cyclic means no degeneracy. It's needed because A cross G is not unital. Okay. And then more interestingly, what will happen is that when we lift the cyclic permutation that plays such an important role in the theory, the lift will no longer be cyclic. Well, this may seem like a problem, but actually this is fortunate because we can use that and play with all these homologies, and that will give this result. Now, I have said that if you prove that two modules have isomorphic localizations, then they're isomorphic, provided there's a map, a morphism between them. This is missing in this case. It can be defined locally, but I haven't found a better way. But I think that some results of Augustin, and I hope to make him work on this, will give the full result. Okay, so I guess, well, I'm not doing that bad, but I'll have to rush a little bit. I'm counting how many minutes do I still have?
So yeah, you have about 10 minutes.
Okay, perfect. I was counting on 9. You're generous. Okay, thank you so much. Okay, so let's look at the case of group algebras. For a group algebra, the Hochschild homology of smooth functions on a compact group is just class functions. This was known, but I forgot, Natsume, I think. And then the periodic cyclic homology, we're in one of those situations when it degenerates very quickly. The SBA spectral sequence degenerates very quickly. And it's just to periodize the Hochschild homology. Okay. This is compatible with localization. And in fact, for orbital integrals, we don't exactly need localization. We need congruence classes. Okay, what do I mean by congruence classes? It's to divide M by an ideal times M. But this turns out to commute with localization, so everything is very nicely behaved here, thanks to commutative algebra. So localization and then taking congruences with respect to M prime commutes with, there are two operations that commute. So it's the same thing as taking congruence classes with respect to M prime and then localization. Now we'll do this, and if we do this for two maximal ideals that are different, in the end we get a big nothing, we get 0. So if we are in this case. However, if M is equal to M prime, again, we basically did nothing because we fall back onto M divided by M. Here maybe you prefer M prime, but they're equal. Okay, so what does this mean us? It means us that if we localize, we don't lose any information from M divided by Gothic M times M. Okay, so we could as well localize at M. And in fact, this is a good idea because this will eliminate some information that is unnecessary. Okay, well, if we think that this quotient, then when we divide a periodic cyclic homology by the ideal of functions that vanish at gamma, this could be interpreted as, well, I'm thinking about them as being orbital integrals in periodic cyclic homology localized at gamma. But then this is the same as for K, and this is then pretty small. Okay, but there are much more results, much more recent and much deeper in some of them were in this conference. Okay, here's a small reason why the above relations hold, but I'm not going to go through that. Okay, so now it's a little bit smoother. Well, this theorem shows that, I like in the discrete case, the relation between, on the one hand, the homology groups of A cross G, and on the other hand, the differentiable homology of G is, to say the least complicated. So it's not so direct. I mean, you can see that even in the case of R, what can be simpler than R. Okay, but here there are again some very nice results of the same authors, Flaum Postumatang, but also there's some very deep work of Kreining and Murdyke on this connection. But this shows that the situation is more complicated for non-discrete groups. And I'd like here to make a parenthesis, since I mentioned this, well, I just explained a little bit my main result. That main result is supposed not to work for this Cohn-Riefel group F theta. Okay? So we have seen that F theta is not algebraic. So I would like to formulate as a question for people who want to kind of sharpen their teeth with these problems, to determine the explicit Hochschild cyclic, even periodic cyclic homology for the group algebra of F theta. Of course, in fact, for the periodic cyclic, there's not much to be done because we can just iterate the result of Elliott, Ness, Natsume. And to help in this quest, it helps to say here that if we look at all this localization in the specific case of A cross R, so G equals R, which is a set of real points of the complex numbers, then the only non-zero localization is the one at the identity that follows from the results from the construction of Elliott-Natsume, as well as from the theorem that I have stated. Okay, so here, well, since I'm kind of running a little bit out of time, there was this discussion about looking at congruence classes, that is dividing by mx. Now, if we localize at mx, that gives us germs. If we quotient by mx, that gives us values. Okay, but that does not suffice. So that's known in homological algebra, that this does not suffice. However, we can be a little bit smarter and take not just quotient by mx, but by all higher powers of mx, and take the projective limit, and then that would suffice. Okay, and the reason why this is interesting is that if you take cyclic cocycles that are supported on a conjugacy class, they will factor through a module like this. So we don't lose anything if we do that. Okay, so there's also the localization, the completion, which is stronger than localization. Fortunately, don't have that much time to talk a little bit, to talk about this. Okay, let me also move quickly through this. We can localize, so I said that localization corresponds to germs. We can also localize at open invariant neighborhoods, and then we obtain a result that happens for discrete groups. That is when we localize near a conjugacy class X, then the periodic cyclic homology becomes the periodic cyclic homology of the cross product with the centralizer. Here, the conjugacy class must be semi-simple, of course. Okay, so there's this analog. In fact, this is a step in the proof of the main theorem, because then we can just localize this at the needed maximal ideal. Okay, but it's nice to know that something that happens for discrete groups also happens for, an important property for discrete groups happens also for algebraic groups. And this, in fact, is true also for Hochschild and period and cyclic homology. Okay, here's one more reduction. Now, of course, cross products by K are still not that easy to deal with. So let's try to simplify that a little bit. So let's assume that we have a connected compactly group, and let's take a maximal torus. And as one does usually in representation theory, we'll take the Weyl-group of this pair. Then the periodic cyclic homology of A cross, this should be K, sorry, copy and paste. The cyclic homology of A cross G is the double invariant part of A cross H. And this uses localization.
So K is equal to G completion.
Here? Sorry?
The K is equal to G in this theorem?
Yes. Here, G should be K. K, K. There's no G in the theorem, only K. I mean, well, there's G by mistake, but there should be K.
Okay, thanks.
And this is also K, sorry. G is K in this theorem. Sorry. Okay, missed that. Okay, for p-adic groups, let me just finish with that. The situation is in fact simpler because there are many open and closed subsets. Also in the case of p-adic groups, there are better results about the connection between the periodic cyclic homology and the topology on the spectrum. For real groups, I don't know if this is true. Okay, but in any case, this is one of the reasons why one looks at the cyclic homologies, because one wants to relate with the topology on the spectrum. And with this, I will stop. Thank you very much.
Thank you, Victor. So let me stop the recording first. Okay.